All right. Good afternoon, everybody. Welcome to Intro to Space Navigation, Spring 2025, Lecture 22. And I mentioned this right before we started the recording, but this is the last Kalman filter lecture. So in Lecture 20, we introduced the idea of the Kalman filter, which is really just sequential estimation, and essentially going through and propagate and then update and then propagate and then update. So I think of it in terms of like you're marching forward through time, left foot, right foot, left foot, right foot. Whenever a new measurement comes in, you'll need to be able to say, okay, here's where I think my vehicle is based on dynamics and our last best guess, and that is propagate. And then you'll be able to say, okay, I have this new measurement that came in. I have to decide how much I trust the measurement update versus how much I trust my gut, which would be the propagate step. You come up with some sort of compromise between those two, and then you go, okay, now we think our state is this. So propagate, update, goes on forever. Or in different groups, you'll hear predict and correct, same idea. So we talked about the general function of Kalman filter, talked about the state propagate step, talked about the covariance propagate step. Lecture 21 was both, we have the state and covariance measurement update. So we have the new state and then the new covariance as a function of the old covariance, and then K, which is the Kalman gain, and then H, and we did a derivation of the Kalman gain, so we have that. And I also talked about the collapsed form. Went through and did a Kalman filter summary. So there's your one pager on how a Kalman filter works. And then talked a little bit about some considerations, did an example, and yeah, we've covered a lot of ground. So you might say, don't I know everything that I need to survive and thrive on the Kalman filter homework that you're about to lob at us, Paul? And to that, I would say, not quite. So I think, well, we will go into a little bit more of gory detail on homework 5, actually, in just a moment. But basically, there is a problem with the Kalman filter, and it won't work for most space applications. And I wonder if anybody caught, I hinted at it at one point. Does anyone have an idea of why Kalman filters don't work in general and we need to do something special to them?
Well, you're dealing with acceleration that isn't necessarily linear. And so with non-linear systems, you're going to need a different kind of Kalman filter.
You got it. Yep, exactly. So it's this line right here. The classic Kalman filter assumes linear dynamics and a linear measurement model. So this kind of, like if anybody took modeling control of dynamic systems or an introductory controls course, it kind of smells like x dot equals ax plus bu and then y equals cx plus du. It's not quite the same thing because that was the new state is the old state times some matrix plus control input times some matrix. Here, this is the estimation version of those equations. So we're saying, okay, the derivative is some linear function of the state plus noise, and we call that process noise. And then the measurement is some linear function of the state plus measurement noise. And then we talked about process noise covariance, measurement noise covariance, and how you ultimately use those to get your state covariance and your measurement covariance. That is great, but all of that builds on this linear assumption. Okay, so maybe somebody else wants to take a guess at it. Y'all have been in college for a while or grad school for a while. Y'all have seen plenty of descriptions about how do we handle nonlinear systems. So here we have a really nicely built up theory behind how to do a Kalman filter for a linear system. So if we don't have a linear system, what do we do? Or what's one thing we can do?
We can try linearizing a nonlinear system to fit this.
There you go. That is exactly it. So the very first thing we're going to do, and this is the topic of today's lecture, is how to take a nonlinear system and linearize it so that the original Kalman filter can be extended to a nonlinear system. And that is called an extended Kalman filter, or an EKF. An EKF is very common in aerospace applications. And if we have time, we'll also talk about the kind of bizarre cousin of the EKF, the unscented Kalman filter, which is the UKF. And then there's some other fancy pants filtering techniques out there. And honestly, filters are an exciting thing to study and definitely something that is still an active area of research. Even though the original Kalman filter publication was in the 1960s, there's still papers coming out all the time about filter tuning and all that. So yeah, it's an exciting thing to be studying. So I just wanted to motivate what we're going to talk about today. We are about to extend the Kalman filter to nonlinear applications. So first, okay, this will be how I do this. So lecture 22 is the extended Kalman filter. But then I'll say first, a practical note on homework 5. So I realize that homework 5 has not been posted yet. I don't want to give you too much anxiety about that. The thing is, you have enough on your plate with homework 4. I don't want you thinking about 2 things at once. So I'm going to post homework 5 this weekend after homework 4 has been collected. But the basic idea is it is going to be a Kalman filter homework assignment. And let me give you just a quick rundown of how the homework is going to look. And you're going to see pretty quickly why the Kalman filter is not going to cut it. So we have the Earth. And we've got this Earth reference frame. And we've got a spacecraft. Maybe I'll use blue for its orbit. That is coming around the backside of the Earth and firing off into space. And so let's say our spacecraft is right here. Yeah, that looks good. Okay. And in this moment, you've got some spacecraft position R. You've also got some observer position. We'll call this P. And then, actually, you know what? We're going to use capital R. And that's going to be following the notation of the orbit determination problem that we did a while back. We talked about, okay, capital R is the ground station, lowercase r is the spacecraft. And so then this vector is going to be R minus R. But you could just as easily use the letter P. It's just our choice of notation. So we're saying that there is an observer, or more accurately, a ground station, at Goldstone, California, which, for those of you that were paying attention, that's one of the Deep Space Network ground stations. Right? And then that gives us, and I don't tell you R, I tell you there's an observer in Goldstone, California. So you compute R. I think I'm nice enough to give you the latitude and longitude of Goldstone, California. So you'll need to go Goldstone, California, lat long to ECEF position, and then take the time ECEF to ECI, and you'll get R in the inertial frame. That's the first thing you have to do. There is a spacecraft with some position and some velocity, which obeys two-body motion. And I believe I'm nice enough to actually give you a full trajectory file, which gives you the position and velocity of the spacecraft over time. And I'm going to take a second, just clean up this rectangle. It's bothering me. Sorry. So that's marginally better, at least. And I'm going to say that Goldstone takes range rate and bearing measurements. That's R3B, range, rate, and bearing. The problem then is write a Kalman filter, or really an EKF, but for now we're going to say Kalman filter, to perform sequential estimation of R and V in the ECI frame. So basically, I'm going to give you a whole bunch of measurements and the initial state, which is wrong. So I'm going to give you an initial state that is incorrect and a covariance that is large, but is larger than the error in the initial state. And what I'd like you to show me is, okay, I'm going to propagate and then I'm going to update, and I'm going to write a filter which will process every single measurement in a great big table that Paul gives me. And then when it's done, I'm going to be able to show, here is my estimate of the state, and here's how close it is to the true state as a function of time. And you'll see that actually your error is going to get worse and then it's going to get better. It's actually, I'd like you to create a plot that looks a lot like this, where you've got your error, which should be close to 0, but it's going to grow and then it's going to shrink. And then you've got your covariance, which is basically error bars, which are going to grow as you propagate and then shrink when you update. So I'd like a graph that looks kind of like this. And we'll make that make more sense later if it doesn't make sense now. And so let's actually go through. I'm going to help you get set up on the homework here. And you're going to see pretty quickly that the Kalman filter won't do this job. So let's talk about the propagate and update steps. Propagate and update. Okay. So I would like to say that the state X is R and V. And I'm going to say R transpose, V transpose, transpose, just to put this on one line. But it's really R and V. It's a 6 by 1. X dot, we immediately run into a problem. The function that computes X dot, so R dot and V dot, from R and V is super nonlinear. So I'm going to write it as a generic nonlinear function, F. So if you have your state and the time, you can use some nonlinear function F to find Ux, but then there is also G. Yeah. So you do have to take into account that process noise. And I'm going to say that acceleration has Gaussian random white noise. Okay. So that means that G, and we kind of talked about this in the example last class, is going to be 0, 3 by 3, and then identity 3 by 3. So I'll give you G. Okay. And then I'll also give you Q. Q is going to be sigma omega squared, identity 3 by 3. So this part is going to look a little bit like the example that we did in lecture 21. So if you remember, towards the end of lecture 21, we went through an example, and I said, well, what if there were no actual dynamics at play? It's literally just noise, right? So there's no acceleration. There's no two-body acceleration. The only acceleration is noise. So G is this 0 and I, and then Q is sigma squared I. So this is going to look familiar. The problem is this F. So we don't know how to handle a nonlinear function that maps from current state to a derivative of current state. So we have F, but a Kalman filter needs capital F. And those two letters, I specifically chose the same letter, but like lowercase and capital case on purpose. We are going to linearize. Okay. Now, the update step, oh boy, I'm looking at my notes. I think I might be being too helpful. Yes, I am. Okay, I'm going to be a little bit more mean. I'm going to have us work together to find what is the range equation, and then what is we'll do bearing, and then what is range rate. So I'd like to hear from 3 different people. Range is the easiest one, so the sooner you key in your mic, the smarter you look. What is the equation for range? So the scalar distance between the ground station at capital R and the spacecraft at little r. I'll give you a hint. Oh, you got it?
I was gonna guess it's just little r minus capital R, as you already have it on the picture.
Well, little r minus capital R is a vector, but I want the scalar, so just the distance.
Oh, then it's gonna be the norm of little r minus capital R.
Exactly right. So there's your range equation. So you can see that when you get a range measurement, rho, you're getting some information about your state because little r is kind of packed in there. You get nothing about your velocity, but that's fine. Because if we had just a filter to propagate range, we already know from our discussion on observability that we would not have enough information to get the full state of the vehicle. And really, with range, rate, and bearing, you're still not getting the full state. You're getting, let's see, the distance and the direction to a spacecraft. So over time, that will give you all of the position information. And you're getting the velocity along the line of sight vector, but you're never getting the tangential velocity, the kind of cross-range velocity. But you actually don't need it. If you get a time history of range, bearing, and range rate, that is enough information to get your full state. So let's talk about bearing. Bearing's also pretty easy. I just want the inertial line of sight direction from capital R to little r. And it's going to look an awful lot like our range equation. They're going to be very similar.
Is it just the the unit vector to the spacecraft?
Yeah, that's literally it. So we're gonna say E unit vector is gonna be 1 over the range, and then in parentheses r minus r. There you go, like that. So it's the same. So imagine you have the vector little r minus big R. The norm of that is the range, and then the direction of that, so the normalized vector, is the bearing. Okay, range rate is going to be a little bit trickier. And so I'll walk you through this part. But basically, you might be tempted to say that rho dot, and I'm being kind of cheeky here, it's not the derivative of this, right? It's going to be a bit different. What we're measuring is the rate of change of your range, but we don't get it by just taking the pure derivative of this equation. It's going to be a little bit different. It is, what is it? Well, you might be tempted to say that it is your bearing dot product with your velocity. So it is the projection of the velocity of the spacecraft onto the line of sight direction. The problem is you would be making a mistake if you didn't take into account the rotation of the Earth. So it's actually not velocity dot product with line of sight direction. It is velocity minus the velocity of the ground station, which is omega cross r, for those of you that have taken dynamics. The rotation of the Earth, so this is the inertial to ECEF rotation, crossed with the ground station position. So this is, inertial velocity of the spacecraft minus inertial velocity of the observer. That gives you their range rate. But then this is the relative velocity projected onto the line of sight direction. There's your range rate. Okay. So I've got those 3 measurement models set up for you. So hopefully we save some time on homework 5. We don't need to puzzle through those. But then immediately we run into a problem. You could think of this as saying that the first measurement is some function of your state and time plus maybe some noise. And then your second measurement is going to be some other function, right? I'm just rewriting this. This is the function. It's 1 over rho r minus r. If you had the state, you could compute it, but it is not linear in any stretch of the imagination, by any stretch of the imagination. Let me be clear. These have tildes. And then y3, actually, now that I think about it, y1 is a scalar. So is y3. So I don't want to confuse you. y1 tilde scalar, y3 tilde scalar. We're going to call this h3 of x and t plus nu3. And all this to say
Would that mean that the mu's in 1 and 3 are also not vectors?
Yep, good call. Good call. Thank you. And Bob, thank you for keeping me honest. So we have these 3 measurement models, H1, H2, and H3, but our Kalman filter needs H1, H2, H3, a linearized model. So again, we will need to linearize. Okay, so we'll talk a bit about how to go through and linearize. Hopefully having this part down makes things a little bit easier. So you can imagine what F is, you can imagine what the 3 H's are, but we'll need to linearize, which involves taking partial derivatives. And I think we might, trying to remember if we have some matrix vector calculus ahead of us, we might. But so just wanted to summarize, Kalman filter, here's how I'll put this. Just for our notes, we need to extend the regular Kalman filter to handle nonlinear dynamics and measurement models, which gives us the extended Kalman filter for EKF. So, time to get into that. EKF. So, in the classic Kalman filter, we focused on linear dynamics. I'm realizing now that my notes are a little bit redundant. Sorry about that. And measurement models. In practice, this is rarely the case. So, to derive the extended Kalman filter, we must linearize about a reference trajectory. Okay, so suppose we start with suppose we have dynamics model which looks like x dot of t is equal to some nonlinear function f of state and time plus g of t omega of t, and measurement model which looks like y, and we'll say y at time k is some nonlinear function h of x at time k plus nu at time k. Okay, so what we need is a way to linearize our propagate step, linearize our update step, and then we're done, right? Then we have extended our Kalman filter. So that's what we're about to do. We're about to have 1 page of notes on linearizing propagate, 1 page of notes on linearizing update. We will take a break. I'll do an EKF summary, and then we'll have 1 page of notes about the unscented and other types of Kalman filters. And then that is the end of the unit. So propagate step. Also, if we have time, which I think we will, I have a fun YouTube video to show you about Kalman filters. So remember, so we're taking this x dot of t, and we're going to start by taking the expected value. So I'm going to say the expected value of x dot t equals the derivative of the expected value of x of t. And that is, we're going to write this as x dot of t. And this is the expected value of the nonlinear function f of state and time plus g of t expected value of omega of t, which is 0, right? On average, our noise is going to be 0. So we can say, all right, our state is going to be a nonlinear function f of x and t. So in plain English, we propagate our state estimate as though it were correct. Okay, so this is the same as the classical Kalman filter, but with no f or phi. Okay, so basically we just say, all right, we're going to propagate our state as though we had the right answer in hand. We accept that we don't, but on average, the noise should cancel itself out, so we're just going to keep moving with that. The hard part is the covariance, right? The state's the easy part. To propagate the covariance, we must linearize about a reference trajectory. And this is where, again, I'm running low on symbols, so I'm sorry. I recognize that when we talk about Kalman filters, we have this hat. We know that means estimated. I know that's confusing. Just to make it even worse, when we're talking about Kalman filters and we have star, that now means reference, not optimal. So I want to be clear about that. Okay, so this is our reference trajectory. So if we take our delta x, we say, okay, this is our true state minus our reference state. And so where is the vehicle minus where do we say it would be before we even started the mission? And then we've also got our delta x, sorry, with a hat on it, delta x hat, and that is x hat minus our reference trajectory. So this latter one is the best estimate of our state minus the reference state. Right? And in this case, if we're subtracting our state, either true or estimated, from a reference, we obtain a difference or deviation. So we can think of deviation as full state relative to reference state. Okay, so the linearization happens right now. Now we linearize. Using a Taylor series expansion. So remember our nonlinear function f of x and t. We're going to say that this is some nonlinear function of our reference trajectory plus the derivative of our nonlinear function with respect to our state evaluated at the state being the reference state. And then this multiplies our delta x of t plus some higher order terms, which we're just going to ignore. And so if you think about this in terms of a vector, so we recognize that the output of this, we're saying f of x and t is going to be x dot of t, right? Which is going to be a vector. But here we're saying, okay, a vector is equal to a vector plus, okay, so all of this must be a vector. Delta x is itself a vector, so this part here must be a matrix. So the derivative of f with respect to x is going to be defined as f tilde of t. So we know that this nonlinear function cannot just without error be simplified to a capital F. So we accept that by dropping these higher order terms, we're introducing some error into the system. That's why we have f tilde. This is the best we can get with a first order approximation. Okay. So let's go back to our original measurement model. So recall, we were saying that x dot of t is equal to some nonlinear function of x and time plus g of t omega of t. Okay, so then now I'm going to say x dot of t is some function of x star and t. So we apply the nonlinear function to our reference trajectory plus f tilde of t, and then we've got delta x t plus g of t omega of t. This first bit I'm going to call x dot star. So what this is saying is this is the derivative of our reference state. Okay, so you can imagine our next step is going to be to subtract, move that to the other side of the equal sign. So we get the derivative of our true state minus the derivative of our reference state is equal to f tilde of t, and then the error or deviation in our state, g of t, t. Okay, but this can then be summarized to, well, this is really just the deviation in the derivative of our state. So delta x dot of t is equal to f of t delta x of t plus g of t omega of t. Okay, so by linearizing, we're now saying, okay, we haven't really gotten back to x dot is equal to fx plus g omega. We haven't quite gotten, I'm going to erase this in a second. Sorry, extra bad handwriting. We haven't quite gotten back to that, but what we've been able to do is we're going to say, well, the error in x is a linear function-ish to a first order approximation of the error sorry, the error in x dot is a linear function of the error in x. And we're going to say that f can now be used to move forward with coming up with our covariance matrix, P. Right? All of this is in service of trying to find P, the covariance in our state. Right? If we just wanted to say, what is my future state given my current state, we would just go ahead and propagate. Just propagate as though it was the right answer. Right? All of our hard work, our blood, sweat, and tears goes into keeping track of our uncertainty in our state. So let's do that. The covariance of the state is P is equal to, we've seen this before now, expected value of, and then we've got truth minus estimate, truth minus estimate transpose. Okay. But observe, I think this is nifty. Let's think about truth minus estimate, right? Truth minus estimate. You could think of this as saying it is x minus x star minus x, sorry, I'm moving too fast. There we go. So all I did was I subtracted x star and then I added x star. So you've accomplished nothing. It's like you're adding 0. Right? But if you group things, you can say x minus x star minus x hat minus x star. And this is our, remember, our deviation. So this is going to be our delta x minus delta x hat. Okay, so by that same token, our covariance can be thought of as the expected value of our deviation minus our estimate of our deviation, and then deviation minus estimate of deviation transpose. Okay. Now this is where we can finally say this looks familiar. Right? This looks familiar because the original Kalman filter had said if we have state minus estimate of the state, state minus estimate of the state transpose, then the solution was going to be some function of f, and I think we had that right. Well, okay, so we've got this form of the solution, or we have the alternate form of the solution, which actually f appears explicitly here. So fp plus pf transpose plus gqg. Or we could say use f to find phi, and then we can say the new p is phi, p, phi. Oh, we should have a transpose. That's embarrassing. And then plus this integral term. So you can look at it either way. And because we've already been through this derivation, I'm not going to run through it again. I'm just going to say, we'll skip to the conclusion here. This should look familiar. We have replicated the classical Kalman filter setup and can now borrow its results. Okay, so there's two ways of solving this. You could say that pk is equal to phi k p k minus 1 phi k transpose. You know what? That transpose looks too much like a plus. Yeah. Plus qk. Or you could say p dot of t is equal to f of t, p of t plus e of t, f of t transpose plus g of t, q of t, g of t, where however you want to do it, this is now going to be f tilde. I'm going to call this phi tilde and phi tilde. You're either going to get f and plug it into the equation on the right, or you're going to get f and use it to build phi and plug it into the equation on the left. I will leave that up to you. But all of these are obtained from linearization. Yep. And that's it. So we propagate our state by using the actual nonlinear state dynamics. Like there's no reason not to just use the equation. We don't need to linearize R. We need to linearize to find P. Or we might say, well, I'd rather find P using some convoluted nonlinear way. You can do that. It's just that's not an extended Kalman filter anymore. Our solution is to say that if we just linearize to find F and then plug that into the equations that we already know, that will work well enough. And that does work well enough. That's the extended Kalman filter kind of idea. Okay, so natural pausing point. Questions on extended Kalman filter propagate step. Oh, cool. Okay. Next is the extended Kalman filter update step. So we begin with our nonlinear measurement model. Okay. So y of k is h of x of k. Oh, yes. Question, Peter?
For the P dot T on the right-hand side there, isn't it supposed to be at the second GT transposed, or am I misremembering?
You got it. Thank you. See, did I have that right the first time? I want to make sure I didn't make that mistake twice. Yeah, okay. Thank you. Appreciate you. Okay. Our measurement model is basically y equals not hx, but h of x, right? H is now a function, not a matrix, with, we already said, the expected value of our measurement noise nu of k is 0. And we also said that the expected value of nu of k transpose is r of k. All right. So if we take the expected value, then we get the expected value of y k is the expected value of h of x plus the expected value of nu k, which we know that this is 0. So this is just the expected value of h. Okay. Which, now we have to be careful. We're getting cheeky here. This is approximately equal to h of x. Okay. So we're saying the expected value of our measurement is the same thing as the expected value of the measurement that we should be able to compute given our state, right? Which is then approximately equal to the expected value of the measurement that we would compute given our best guess of our state. So this is the truth, and this is current guess, just to be clear. So we do have to be careful. This is also a first order approximation. Okay. So as with the classical Kalman filter. Oh, Peter, did you have another question, or is your hand just up?
Thank you for reminding me. I accidentally left it up.
No problemo. As with the classical Kalman filter, we construct an update equation. Which looks like this. X hat plus at time k. So this is after update at time k, best guess. That's our notation. Is X hat minus plus Kalman filter gain, or Kalman gain, k of k. And then we've got measurement minus, okay, this is where we got to be careful. Ordinarily, this would be y minus hx. Now it's y minus little h of x. Hopefully that makes sense. Okay. Now what we're going to do is we're going to subtract the reference trajectory from both sides. So we're playing this game again. I'm saying x k plus minus our reference trajectory is equal to x of k minus reference trajectory plus Kalman gain measurement minus the measurement that we would expect based on our best guess. Where now this is another deviation. We're going to call this delta x hat k plus, and this is delta x hat k minus. Okay, so our equation becomes delta x hat k plus equals delta x hat k minus plus Kalman gain measurement minus what we would expect if we were correct. Okay, so now again, because we are linearizing, we're really not writing a filter to track our state anymore. We're writing a filter to track this deviation, or how wrong we are from what we would expect to see. Okay, so now here is our update equation. To find the optimal gain k, we must linearize. So there's nothing wrong with a nonlinear state update equation. The same way there's nothing wrong with a nonlinear state propagate equation, right? And I really should go through and box these in red. I'll do that in a minute. It's the Kalman gain and it's the covariance that's going to get us, right? So we do need to do some linearizing here in a moment. So to find the optimal gain k, we must linearize. Y is equal to h x plus nu. And I'm going to say that this is approximately equal to, and we've got, okay, h of reference trajectory plus, same game, the partial derivative of our nonlinear measurement function with respect to the state. And this is going to be a matrix evaluated at the state being the reference trajectory. And then this multiplies our deviation, x, plus some higher order terms, which we're choosing to ignore, plus that nu, right? Where this derivative of h with respect to x, we're going to call h tilde, where again, we've introduced some error because of this linearization. So it's first order approximation. And what we're left with is basically that y minus h of x. So now on the left-hand side, we're saying this is the deviation between our measurement and the measurement that we would expect if we were at our reference point, not the truth, not the estimate, but the reference. So there's kind of three players here: truth, estimate, reference. This is equal to h tilde and then deviation in x plus nu. So we have recovered another linear equation. So we are back to a linear measurement equation. Okay. So I'm just going to say for now, skipping several steps. I don't feel like going through the derivation from the last lecture. Just going to show you without derivation that the extended Kalman filter Kalman gain is pk minus hk transpose, and then we've got hk ek minus hk transpose plus rk, all of this inverse. And we have the Joseph form and the collapsed form of our update equation. So the Joseph form, which is kind of the favorite one, is pk plus is I minus kk hk, and then pk minus I minus kk hk transpose plus k k r k k k transpose, or the collapsed form, which is kind of dangerous. You're inviting numerical issues, but might be easier to implement, fewer steps, is going to be I minus k k h k ek minus. And then we go through and we say, okay, but now it's linearized, 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 and linearized. So I guess technically that makes this linearized too. So linearized, 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 linearized. Where, wow, I'm gonna try a little harder here. Where hk is obtained by linearization. Okay, and that's it. Those are our extended Kalman filter equations. So maybe I'll go through and draw some boxes now here. And then, yeah, we'll take a break in a second. I'll go through and make another one-pager like I did in the middle of lecture 21, where we say, here's all of the Kalman filter. We're going to do that again in a second for the extended Kalman filter. Let's see. These equations deserve a box. The fact that I write on a slant is becoming more obvious when I actually try to go through and put a nice clear rectangle on it. There we go. There we go. So there is our state and our covariance propagate, or sorry, our update equations. Our propagate equations are going to be here. Whoa, nope. Trying to draw a box. Okay, one thing at a time. Nope. And where was our, there it is. That's it. Okay, questions on the extended Kalman filter, or otherwise we'll take a 5-minute break. Okay, let's take a break and come back at, let's say, 7:06.
Did you mean to stop sharing there, or?
Oh, sorry. Are you? Do you need the
Yeah,
notes up?
I ended up being a bit behind with the notes.
Stand by here. Yep, there you go.
Thank you.
All right, we all good with the notes? I'm gonna stop sharing for a sec. All right, welcome back. So as promised, I owe you a summary of the extended Kalman filter, and we're about done with our Kalman filter unit here. So this is our EKF summary. I'm going to try to fit this on one page. Hang on. Oops. Oh, that's sensitive. Okay, that'll do. So again, we initialize. Ooh, I'm going to write smaller. I want to fit it all on one page here. Initialize at T naught is equal to 0, x k minus 1 hat plus is x0, and then we have p k minus 1 plus is p0. So it's up to me, or it's up to someone else, to give you your initial state and covariance. It's only your job as filter engineers to propagate and update. Okay, so the next thing we do is we gather a new measurement at time tk. And so that's going to look like yk, which I'm going to draw as a vector, but it could be a scalar, and then some measurement covariance rk. This is where you got to be careful. If you have a filter which is handling multiple different types of measurements, which most of them do, and certainly you will on homework 5, then you'll need to be able to recognize what type of measurement you have and go, oh, okay, I'm going to use this measurement model and this R, measurement covariance matrix. Okay, so from here, we propagate state and covariance from time t k minus 1 to time tk, where the new star of the show, f tilde, is going to be the derivative of our nonlinear function with respect to the state. And this is going to be evaluated at our state being our best guess of our state. So you're going to take this derivative, you're going to be building a matrix. Some of the terms in the matrix are going to be dependent on your position and velocity. So you just plug in your current best guess. That's the idea. So from there, you could say that your state dot is f of x t. And you can linearize if you want to, or sorry, you can compute the state transition matrix if you want to. And then your covariance is going to look like pk minus is equal to phi from k minus 1 to k, p k minus 1 plus phi t k minus 1 to tk, transpose plus qk. Or you could say p, oh, almost started to do the vector, p dot of t is equal to f tilde of t p of t plus p of t f tilde of t transpose. I guess these phi should also get tildes. Plus g, wow, I am all over the place. Sorry about that. Got g of t, q t, g of t transpose. So this is the propagate step, and then we've got the update step. State and covariance. With new measurement. Okay, where part A of update is linearize our measurement model to basically get an approximated measurement sensitivity matrix. H K tilde is the derivative of H with respect to our state, evaluated at our state being our current best guess of our state. And then from there, we compute the Kalman gain. Which would look like K is equal to PK minus HK transpose. And okay, just wanted to make sure I didn't lose track of my notes. We've got HK tilde PK minus HK tilde transpose plus RK -1. Then we update our state. Which is going to look like XK hat plus is XK hat minus plus KK got Y minus, no reason not to use the full nonlinear equation here, and this is XK minus. Okay. And then finally, we've got our update covariance. Which is going to be PK plus is equal to I minus KK HK tilde PK minus I minus KK HK tilde transpose plus KK RK K transpose. And then we loop back up and we'll say K equals K plus 1. So we're incrementing time. And we loop back up to here. So this should look similar. Yep, looks pretty darn similar to what we had before, except now we have our crucial differences is that this is different and we have to linearize, so that's different. And then this is different. Well, I guess technically every equation is different, but those are the ones that I really want to draw your attention to. Great. Questions on the extended Kalman filter? Otherwise, we'll move on to the next thing. Good to go? Okay. So before we move on, I probably did this in the wrong order, but when I took the equivalent of this class when I was in graduate school, the professor, Dr. John Christian, showed us a YouTube video to basically make Kalman filters, or really just navigation in general, make as much sense as possible in as little time as possible. So I queued up the same YouTube video to show you. It's only a minute long. I'm hoping that showing a video through Microsoft Teams streaming doesn't cause like heaps of bandwidth issues. We'll see how it goes. But anyway, this is everything you need to know, not necessarily about filters, because it's a little bit different. This video is about missile guidance, but I just love how crisp and clear this video is. So hopefully the audio comes through. Let me know if there are any issues.
I'm not hearing anything. I don't know if you've started it, Oh,
Yeah,
but
started
I
a
can
while ago.
hear this I can hear this video in my soul. I've heard it about a million times.
Yeah, I was gonna say, like, this is okay. Hang on, let me try to fix the. Trying to think. Why would the sound settings? Okay, stand by. Hang on. This is really funny, and it's totally worth the wait here. Let me pause my screen share. Stand by. We're gonna get this fixed. I wonder if this will make a difference. I'm resharing. Aha. In that case, maybe this will work. If I put this through my headphones. Okay. Somebody give me a thumbs up if you can hear this.
The missile knows where it is at all times. It knows this because it knows where it isn't. By subtracting where it is from where it isn't, or where it isn't from where it is, whichever is greater, it obtains a difference or deviation. The guidance subsystem uses deviation to generate corrective commands to drive the missile from a position where it is to a position where it isn't, and arriving at a position where it wasn't, it now is. Consequently, the position where it is now the position that it wasn't, and it follows that the position that it was is now the position that it isn't. In the event that the position that it is not the position that it wasn't, the system has acquired a variation. The variation being the difference between where the missile is and where it wasn't. If variation is considered to be a significant factor, it too may be corrected by the GEA. However, the missile must also know where it was. The missile guidance computer scenario works as follows. Because a variation has modified some of the information the missile has obtained, it is not sure just where it is. However, it is sure where it isn't, within reason, and it knows where it was. It now subtracts where it should be from where it wasn't, or vice versa. And by differentiating this from the algebraic sum of where it shouldn't be and where it was, it is able to obtain the deviation and its variation, which is called error.
I just get a huge kick out of that. So, anyway, that is clear as mud. That is hilariously not clear what they're talking about in that video. But they use a lot of the buzzwords that we use. And technically, that is a guidance algorithm instead of a navigation algorithm. But they are topics next door. So now, hopefully, if any of you are familiar with the missile guidance system memes, they make a little bit more sense. They didn't show the video at Raytheon. That's a crime. They should show everybody that one at Raytheon. Okay, so the last thing I want to discuss, and this is kind of a for your information topic. It's going to take about maybe 10, 15 minutes to get through, and then we're done, is an alternative to the extended Kalman filter, which is called the unscented Kalman filter. Okay, so we said before the original Kalman filter assumes linear dynamics and a linear measurement model. So the EKF deals with nonlinearity. By linearizing. Seems reasonable. Okay. This is generally okay, but can be a bad idea. For example, if F or H is highly nonlinear. And that makes sense just in general. Sometimes you can't get away with linearization. Sometimes it's just too much. So there is another way to look at this. So the unscented transform or UT is a method for calculating or estimating the statistics of a random variable. Okay. So there's 3 steps to this process, but I want to make sense of why we're doing this, right? The whole goal of the Kalman filter is to be able to say, based on where my state was and my dynamics, here's where I think it is. So you're propagating a state in a covariance. And then based on this new information that I just received, I can update my state and my covariance. But either way, what you're really doing is getting the mean and covariance, which is a higher order form of a standard deviation. You're basically getting the mean and standard deviation of an n-dimensional system. And we're estimating that by saying, okay, it was Gaussian to start. We put it through a linear system. Now it's Gaussian on the other side. But the thing is, it's not really a linear system. So what you could do is approximate the linear system as a nonlinear system, or you could say, let's use a completely different method of estimating the mean and standard deviation of the output of a function, which isn't just linearizing the function, and that is the unscented transform. The way you do it is you compute what are so-called sigma points. Sigma points. And there are going to be 2n plus 1 points where n is the dimension of the problem. Okay. You pass these through the nonlinear transformation. Like f or h. And then you approximate posterior statistics based on where these end up. Okay. So the way I like to think about it is you start with a system that looks like this. Let's say this is x. And we know that the mean of x, so our best guess of our state is at some point. But then we've also got some covariance, which maybe looks like this. Okay. What I'm going to do is I'm going to select 6 sigma points, 1 in the middle, and then we're going to do the sides. Sorry, did I say 6? I meant 5. So for a 2D problem, 2n plus 1 is 5 sigma points. So sigma 1, sigma 2, sigma 3, sigma 4, and sigma 5, which are chosen around the distribution, basically the major and minor axes of the covariance. And you're saying, okay, these are all points in space. These are all other states, right? So we've got our best guess of our state, and then in this case 4, but it varies with your dimension, other guesses of our state. Rather than estimating that the output Gaussian is some linear function of the input Gaussian, let's just actually run every sigma point through some function, y equals f of x. When we do that, we're going to get 5 or some other number if it's a higher order problem. So now we're in output space. let's say that they output to here, 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 and here. Okay. Well, there's your output covariance, right? So we didn't say that the output covariance is some linear function of the input covariance. We said the output covariance is just found from the sigma points. Like, why don't we just either propagate or update the sigma points and then back out mean and standard deviation after the fact? So without going into any more gory detail, that is basically what's going on under the hood with the UKF. So I'll give you a quick UKF propagate and update discussion. So UKF propagate and UKF update. Okay. So the first step is to calculate sigma points, and there are also associated weights, which I kind of left out, but these can be computed cookbook style. Then you propagate the sigma points. So you put them through your propagation function f, and then you use propagated sigma points to approximate your state and covariance. Okay. And then for the update step, you again calculate some new sigma points and weights. You compute expected measurements for all points. Okay. You construct a Kalman gain. And then you update to find xk hat plus and pk plus. So one final thought, the unscented Kalman filter, or the UKF, is more capable of handling highly nonlinear systems. Sorry, more capable of handling highly nonlinear systems. And does not require taking partial derivatives. So you might say then, why don't we just use this all the time? Well, however, it is essentially heavier and slower. Than an extended Kalman filter. Okay. So the extended Kalman filter is, if you understand your system fairly well and you can get away with linearizing your system, the EKF is going to run faster. And the thing is that not being willing to take partial derivatives should not be a deterrent, right? Like, we're paid to do math, or if you're not working now, you will be paid to do math. So just go take the darn partials. So that's not really the deterrent. The UKF is it really shines when you have a system where the EKF starts to fail. I wouldn't sub it in for any other reason. And the UKF is also slower, and generally flight computers are hilariously behind the times because they need to be radiation hardened. So flight computers tend to be pretty puny, and we're really just trying to save all the processing power that we can. So I prefer the EKF. We're doing an EKF on homework 5, but you should be aware of the UKF. There's also a really neat little thing. I'm going to give you like 2 bullet points on it, and then we'll stop. It's worth talking about. This is kind of on the cutting edge of filter technology. something called anonymous feature processing, or AFP. And this is brand new. So in the last about 5 years, an exciting new filter paradigm has emerged. Which implicitly handles the data association problem. So everybody who's currently waist deep in homework 4, putting together their own star tracker, you recognize that the very hardest part of a star tracker is the data association problem, which is star ID, right? Now, I'm kind of keeping this bland and generic, but if you have a filter which is processing measurements of different points in space, those could be line of sight directions, those could be distances, I'm keeping it really generic. But basically, you're taking measurements about things, and it can be very difficult if you're getting measurements in parallel to correlate them, to go, okay, this point which I'm measuring is this point in 3D space, and that point which I'm measuring is that point in 3D space. It becomes a bit of a bummer. So anonymous feature processing, which relies on finite set statistics, you can simply and the filter measurements and a catalog. And it will figure out which is which. Pretty snazzy. It seems like magic. It's actually surprisingly simple and efficient. And the paper, if you want to go read more about it, is anonymous feature processing for efficient onboard navigation by James McCabe and Kyle DeMars. So I encourage you to go read more about that. Definitely pretty snazzy. It is beyond what is necessary for this class. But just want you to be aware that Kalman filters are still an alive and well area of research, and there's some really cool snazzy stuff out there. But the main thing that we'll be focusing on for homework 5 is this extended Kalman filter in the context of a range rate, and bearing problem of a spacecraft that is on its way out to the moon. So with that, any questions about the EKF? Otherwise, I'll stop the recording and we can turn this into a little mini office hours. Okay, thanks everyone for sticking around. Class is dismissed, but if you have questions on homework 4, I will stick around and help for at least the next half hour.